If you've seen my video, The Story of the Earth Made Easy, you'll know that by the mid-19th century, geologists had a pretty good idea of how the rocks on Earth had been laid down. They understood the process of sedimentation, which deposited the shales, sandstones and limestones that we see all around us. They understood uplift and erosion, the principles by which mountains are formed and new sediment laid down. And they understood volcanism, faulting and folding, which altered the beds and created new landforms. But as usual in science, the more they understood, the more questions they had. Some things just didn't fit this tidy pattern. Huge boulders were in places where they shouldn't be. It was as if a powerful giant had picked up massive rocks and deposited them hundreds of miles away on top of completely different strata. Then there were the huge U-shaped valleys of northern Europe. They didn't make any sense. Valleys are cut by rivers and form a familiar V-shape. Early geologists assumed that these features were caused by the biblical flood. But geologists Jean de Charpentier and Carl Friedrich Schimper, who had been studying glaciers in the Alps, realized that these features were completely inconsistent with a flood, but they did fit perfectly with glacial formations. Glaciers are just accumulations of mountain snow, compacted under their own weight to form slabs of ice. Under gravity, these slabs move slowly down valleys until they reach lower altitudes where they melt. As long as the amount of snow falling at the top is balanced by the amount of ice melting at the bottom, the glacier is in equilibrium. It looks as though it's standing still, but in fact it's moving very slowly, at the proverbial glacial pace. De Charpentier and Schimper noticed how these glaciers broke off rocks from the valleys through which they travelled, carried them downhill, and then deposited them at the lower slopes during melting. Where the glacier melts, it also drops its assorted load of pebbles and gravel in piles called terminal moraines. This mirrored perfectly unexplained features found all over much warmer parts of Europe. One man, Louis Agassiz, recognized these features in northern Europe as undoubtedly the result of glaciation. And if that was true, Agassiz realized that northern Europe had not only been subjected to glaciation in the past, but glaciation on a massive scale. This wasn't a few glaciers moving down valleys, but whole ice sheets moving across a continent. Not surprisingly, this radical idea was initially dismissed by geologists who clung to the biblical story of a flood. But as always in science, the evidence eventually becomes overwhelming. A great flood simply didn't explain a host of odd-looking features that dot the landscape of northern Europe and North America, and which mirror exactly the glacial valleys of the Alps and Scandinavia. We see huge freshwater lakes, often trapped by terminal moraines, lateral moraines and tills, coals scooped out by ice movement, abrasion marks caused by the scraping of glaciers and their rock loads, hanging valleys, arêtes, rock steps, rock basins, isostatic uplift, drumlins and kettle holes. All the remnant features we see in the warmer landscapes of today are identical to the features that we know are caused by glaciation. Drill down into the peat bogs and lakes and you'll find the biological evidence in pollen and fossil remains. In Europe, for example, as the climate cooled, species of trees like oak give way to pine and then birch. The skeletons of warmer climate creatures like boar and deer give way to cold climate animals like moose, elk and mammoths. And there's another piece of evidence that has huge implications. During the Ice Age, sea levels fell. Around 10,000 years ago they rose again when the ice melted, drowning valleys and cutting off areas of land. The Bering Strait cut the land bridge between North America and Asia. Indonesia and Britain were isolated, and as we've seen in Human Ancestry Made Easy, all this changed human migration and settlement patterns. The rise in sea level must have flooded coastal settlements all over the world. There perhaps is your mythological flood, a flood that may have had devastating consequences for coastal dwellers, but in global terms was limited. Hardly surprising that a flood figures so heavily in mythologies. At its height the ice covered 1/3 of the Earth's land surface and was a mile thick. But Agassiz and his contemporaries still had no idea when all this occurred. 130 years ago even the age of the Earth wasn't known, and geologists could only guess at a few million years based on the depth of sedimentary rock they found. Since these glacial features were sitting on top of this pile of sedimentary rock, the Ice Age had to be very recent in geological terms. As we've seen in the Age of Our World Made Easy, dating techniques are numerous and various. No single technique is used in determining age. Dendrochronology, carbon dating, DNA markers, fossil dating, all these standard techniques can be used for determining the age of flora and fauna associated with the advance and retreat of the ice. These results can be cross-checked with each other, and with a technique designed specifically to look at the Earth's past climate, ice cores. Since more snow falls and freezes in winter than in summer, ice cores from all over the world can be dated like the rings on a tree. Then they can be correlated with each other to see not only if one year was colder than another in a particular locality, but if it was colder on a global scale. Another technique is to measure the ratio of oxygen-16, the stable form of oxygen, to the isotope oxygen-18, or O18. It works like this. Water evaporates off the tropical oceans and is carried northwards and southwards by prevailing winds. Most water molecules are made of 2 hydrogen atoms and a single O16 atom. But sometimes the oxygen atom will be the heavier isotope O18, and that makes the water molecule heavier. Being heavier, O18 water needs more energy for evaporation, and when it meets colder conditions, it condenses more readily. So when it's warm, more O18 evaporates and more of it reaches the poles. When it's cold, the reverse is true. So by measuring the ratio of O18 to O16 during annual snowfall, researchers can assess the global temperature for that year. A higher ratio means warmer weather. As a result of this methodical sample collecting and dating, in the 20th century, geologists uncovered not only more evidence for an ice age, but a series of ice ages. The temperature warmed and cooled several times by as much as 10 degrees. The temperature difference may not seem like much, but on a global scale this represents a massive change in the quantity of heat reaching colder latitudes. Going through the Earth's sedimentary layers hundreds of millions of years back in time, geologists have also discovered other ice ages. The oldest occurred at the end of the Proterozoic era, 1.1 to 1.4 billion years ago. There was another at the end of the Ordovician, 445 million years ago, and again in the late Carboniferous, 310 million years ago. So what caused these changes in temperature? One thing these ice ages have in common is that whenever they happen, a large continent is lying at one of the poles. As we've seen in the story of the Earth Made Easy, the Earth's crustal plates are constantly moving and the continents change position. Antarctica wasn't always at the South Pole. The fact that its sedimentary layers include coal and warm water fossils suggests that it was once much further north. But although the position of Antarctica may set the right conditions for an ice age, it doesn't explain the trigger. Once the trigger is pulled, the Earth goes into a vicious circle. As temperatures drop and ice cover increases, the ice reflects more sunlight back into space, lowering the temperature further and causing more ice and the reflection of more sunlight. When the trigger begins a slight warming, some of the ice melts and less sunlight is reflected, causing more ice to melt, and so the vicious circle reverses. What's the trigger? Throughout history, a number of things have been suggested. Dust in the atmosphere reflecting sunlight and cooling the Earth is one possibility. So is a wobble in the Earth's orbit, decreased solar energy, or a shutdown of the ocean current that brings warm water to the North Atlantic. But the most worrying conclusion of all is that the ice ages were sparked by changing levels of carbon dioxide in the atmosphere. It's critically important to understand this process. We're lucky enough to live in a benign climatic environment, an interglacial period that's not too hot and not too cold. In 2004, a study based on a record ice core looking back over 740,000 years found that our current interglacial is very similar to interglacials that occurred more than 400,000 years ago and lasted around 28,000 years. That means the benign conditions we enjoy could last another 16,000 years, provided nothing goes wrong. But the same ice cores show that something is going very wrong. In the next video, I'm going to look at the Earth's past climate and its future.